Hello and welcome. Thank you for joining this seminar and thank you for your interest in my work. My name is Artem Poliviani and I'm a senior lecturer here at the School of Computing and Information Systems. And one of my research areas is process mining. And process mining is a discipline that aims to improve real-world processes based on their historical executions. And today I will talk about very recent developments that I am involved in on measuring generalization of process models automatically discovered from event data. I will present an approach for bootstrapping the measurement of generalization of the discovered process models, and note that the term bootstrapping here is used not in the common computing sense, like to boot a system, but in the computational statistics sense, when we use computational methods to establish a measurement using the data that we have at our disposal. So I will also present the context of the problem. So I'll spend some time to talk about process mining, to introduce you to the field. And also then within this context, our recent results that led us to the idea of measuring generalization in the way that I'll present to you. Okay, enough said. Let's proceed with the slides. So process mining has a history of approximately 2 decades, and this field was introduced and heavily developed by the group of Will van der Aalst, who is now in Germany, Aachen, but previously he was in Eindhoven, the Netherlands. And the environment, the context of process mining is shown on this slide. So the idea is that, okay, we are all living in the real world, right? So we all live in a real world that we want to improve. And one way we decided to improve this world is by creating software systems. So we developed software systems that support and control what is happening in the real world. And these software systems, they record logs, event data that denote what happened in this real world. And also these software systems, they are heavily driven by so-called process models. So models that describe possible behaviors of software systems. And process models, they specify what software systems should do, but also software systems implement these process models. So for example, if you think about process models, this can be business process models like BPMN models. It can be even software code like programs, right? So they also describe processes. And these models, they also represent or describe what we expect to happen in the real world. So if we look at this picture, it's kind of strange that this event log, this event data is put aside, and this is exactly where process mining fits in. Comes and says that, okay, let's use this data to improve the way processes happen in the real world. And process mining does that by means of three main problems, I would say, which is process discovery, conformance checking, and process enhancements. So in process discovery, we take event logs, event data generated by software systems, and we try to automatically construct process models that represent that data well. In conformance checking, we say, okay, we have a normative model, a description of how we expect the system to behave, and we have real data generated by the system, and we want to compare and find deviations, commonalities between what was designed and what happened in reality. And process enhancement is then the way to improve models by means of the data. So we have models, but we learn from the observed data, and we try to improve to be models so that then they drive our software systems to better performance in the future. So this is the context of process mining, and event logs is kind of the main driver. You see that it's an input to all the problems that process mining addresses. So if we accept that mythological viewpoint that the world rests on three whales, then we can also say that process mining world rests on three fundamental problems of process discovery, conformance checking, and process enhancement. More recently, other areas emerged, right? So there are more recent problems addressed by process mining researchers as well. So, for example, we had a PhD student who recently submitted a thesis on the topic of robotic process mining, where we try to automate the generation of RPA scripts, so automation of monotonous, so to say, routines at organizations. Process forecasting, another fairly recent topic is agent system mining, where we also have a PhD student who recently started working here, where we try to discover models that are models of agents interacting that represent the processes that happen in the real world, etc. But again, I stress that three main problems are process discovery, process enhancement, and conformance checking. They were also the ones that stood at the origins of the process mining area. All right, so I said that event logs are very important. Event data is very important. That's oil of process mining. So let's take a closer look what a typical event log is. So event log is a collection of events. We can, for example, represent them in a table. As you see on this slide, each row corresponds to one event, and in process mining we kind of agreed through time that each event should have at least three attributes, right? And these attributes are case ID, timestamp, and action. So case ID refers to a particular instance of a process. So for example, if you're talking about loan application process, that can be events that share the same case ID can refer to a case of handling one loan application, for example. A timestamp is a time point at which an event occurred, and action is action that triggered the event, right? So these are the three common attributes. We kind of expect that every event log, every event in every event log will have these three attributes. And of course, we can think of further payload, further information that can be attached to the events. Sometimes we also record resources, human and technical resources that participated in the actions that triggered the event. We can also record information about objects that were used to execute an action, etc., etc. And then you can imagine that we can use different, different further analysis if further data is available. So this is a typical event log, and we also can have a different perspective to it. We can see an event log as a multi-set of traces, right? So here by trace, we refer to all events with the same case ID, right? So for example, here on the right-hand side, you see two traces extracted from the event log, and they're also ordered by their timestamp. So they describe the evolution of the process instance that was happening in the real world. So for example, if I look at case one, and I'm kind of continuing with this example of loan application, it can be that A is a request for a loan, B is an activity of assessing the loan feasibility, so to say, C is closing the loan, and F archiving the loan, or something like that, right? To give you some link to some tangible real world example. Of course, traces can repeat multiple times, right? So that's why I'm saying and stressing that event log is then a multi-set of traces. So here, for example, this case one, that is, it's not case one, case, case one, A, B, 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 C, F happened 5 times, right? So that's why we denoted multiplicity of 5 for that trace. All right, so this is the data we are working with. To talk a bit more about the problem of process discovery, introduce you this topic a bit further. So in process discovery, we take these event logs, these multi-sets of traces, and we construct process models, and we aim to construct good process models that describe those processes that were recorded in the log. So process models can take different shapes. So here, for example, I have what we call directly follows graphs, DFGs, in process mining. So a graph describes a process. So I and O are the input and output nodes, and we can think of a particular trace as a walk from input to output node in this DFG. And there are different notations. Of course, concurrency is very important. We try to also discover concurrent actions. So then we discovered models as Petri nets or BPMN, business process model annotation, diagrams, etc., etc. But for the purpose of this talk, it will be sufficient just to understand process models as graphs. So, well, some concepts that describe traces. Of course, this goodness of models is a thing to understand, right? What do we accept as a good model? In process mining, we also kind of over time agreed that there are 4 dimensions that estimate the goodness of discovered models. So we say that a model should describe as many as possible of the traces recorded in the log. So then we are saying that the model has good recall. So for example, this model over here describes trace A, D, E, E, F. I can have a walk A, D, E, E, F in my model. So that's good for recall. Also, we say that models should allow as few traces as possible that are not present in the log. And then the model has good precision. So for example, the log contains a trace A, D, D, E, F. Of course, that trace is not allowed in the model. So kind of that trace contributes to the badness in terms of precision. But well, we can allow that, but we try to decrease the chances of the traces in the model that were not in the log. Models should be simple, and that can be understood also in many ways. Simple to understand by humans. It shouldn't be overly complex, not large, complex graphs. So we can kind of assume this model is fairly simple, but there are specific measures that estimate the simplicity of models proposed by process mining researchers. And also, models should have a good generalization, we say, and so models should allow traces that may stem from the same process, but not present in the log, right? So a log is kind of a snapshot of what system was doing in the real world. And if the system in the real world continues to live and execute traces, then our log, our system that we discovered should kind of, by magic, by some black magic, be able to accept those traces. So if we discover a good model in terms of generalization, that model should also be able to account for those future traces. And generalization will be the focus of this presentation. I'll talk about generalization, well, closer to the end of this presentation of the seminar, and I will share with you ideas how we approach measuring generalization. So to show you some examples of discovered process models and how things can go wrong in process mining, of course, I hope you understand that this is not an easy task to discover process models. So these are examples of spaghetti models, and we call them spaghetti, well, because they look like spaghetti. So here on the left, the model on the left is a book, example from the book of Will van der Aalst. And spaghetti model on the right is a model discovered by one of my PhD students who actually, well, discovered this model when he started investigating process discovery problems. So one of the first shots to discover a model. Of course, these models will be probably very fitting and very precise, but of course, you probably understand that these are not simple models, and generalization is questionable, right? We don't understand, do these models generalize well or not? But probably they are precise and fitting, so actually overfitting well, because they have so many passes and so many traces that they represent. These are the examples of models from industry. That's what models discovered by commercial tools look like. So what the commercial tools try to do, they try to carve well, some structured, or what we call lasagna process models from those spaghetti models, and try to balance precision, recall, simplicity in a reasonable way, because these models are then consumed by business analysts for decision making. So, right, so these models are constructed, they represent what was happening in the businesses, and then decisions are made to how to improve to-be processes. And these graphs can look very simple, but you need to understand that there is multi-billion business behind this. So one of the graphs in this slide comes from a commercial tool which was recently valued $11 billion. But also we understand that from academic point of view, still a lot can be done in this area, and there still can be many improvements proposed in the area of process discovery. And also recently we had a paper which demonstrated that and kind of requested the community to become more active in the area of process discovery and address the challenges of process discovery. So you also see, well, the title and some background information, that paper on this slide. So let's take a different perspective to the whole problem of process discovery and the quality of process discovery. I mentioned 3 artifacts, so let's take a closer look at 3 artifacts that participate in this problem of process discovery. So it's a log. Well, actually, first, let me mention a system that generates a log. So we have a system, we have a log that was generated by our system, and then we have a model that was discovered from a log. And we can understand each of these artifacts as a collection of traces. And then if we use a Venn diagram to demonstrate these 3 artifacts in the most general way, that's the picture that will evolve. So we have 3 sets of traces described by a system, traces described by a model, and traces, well, that happen to end up being recorded in the log. I can probably agree with me that I can motivate each of these areas on this Venn diagram, that there can be good reasons why traces can end up being in certain segment of this Venn diagram. So I'll not talk much, but for example, if I look at area 1, well, these are the system traces that the system can generate, but system cannot generate, but they end up to be in the log, perhaps by an error, right? Or maybe because this was a workaround by some worker that decided, okay, this is now a more optimal way to handle certain case. And so they end up being included in the log and also end up being discovered and present in the model. Well, because maybe they were frequent traces in the log, and the discovery algorithm that was used to construct a model from the log, well, decided, okay, it's a frequent trace, it's a important trace, so let's reflect that trace in the model. But it was not the trace supported by the system. Okay, so that's kind of the setting. And then within this setting, in 2014, Aalst, Buijs, well, his collaborators, Aalst Buijs was a PhD student of Will van der Aalst as well. They came up with the idea how to then assess the quality formally in process mining. So we have 3 collections of traces, and then, well, it's quite reasonable that we can compare them pairwise. So we can, let's say, take a model and a log and measure precision and recall of between model and a log. So we can overlap those sets, right, and measure the cardinality, and then take as a fraction of what is common traces and to the overall traces, for example, in the model or log. And you can do it between every 2 pairs of artifacts here. So we kind of can end up with 6 measurements that will establish the quality of our process mining exercise. Quite a reasonable approach. So looks nice. If not, well, 2 caveats, 2 aspects that we need to highlight. We need to say that in real world, if we kind of take real world assumptions, we would not know the system. So system is actually unknown to us. Well, you can say, okay, maybe we have a software code implementation of a software system, so the model can be available, but in general, it can be even if the system is available, so code of the system is available, implementation is available, the particular way the users use that system is not, well, it's hard to anticipate, right? You can have a system with all the functionality available, but how actually will the users use the system and how, which combinations of features of the system they will choose to enact, it's kind of questionable. So in general, we use, in real life, we don't know actual system. And also, even if we know the system, probably it kind of describes infinite amount of possibilities, how different actions can be composed. And also a model, discovered model, usually describes infinite collection of traces as well. So here I have these small loops and, well, actually combinations of loops, not just by chance, but to make a point. So this small model also describes an infinite collection of traces. So first of all, these 2 assumptions will need to be relaxed. And maybe you had this experience in your research. So if you work in academia and did some research in the past, I'm sure that you have experienced that once you start taking realistic assumptions in your research, then that carefully constructed house of cards or house of your assumptions that you have constructed starts to collapse, right, and starts to fall. And similar phenomena happens here. So if we take these realistic assumptions, that then many things collapse in this nice scenery that I portrayed to you. So if a system is unknown, of course, we cannot measure many of those 6 measurements. So we cannot, let's say, well, measure the cardinality of a set S. Well, we don't know it. Also, well, if sets M and S are infinite, so describe infinite collections of traces, well, we cannot really establish cardinality. Well, we can establish cardinality, but we need to adhere to some definition. What is the cardinality of an infinite set? And then all the systems that describe, all the systems and models that describe infinite collections of traces become uncomparable. So only, well, the only thing that we can really measure in this case is model log recall, because, well, log is always finite, and then also an overlap between model and log will be a finite set, and we can measure the cardinality of that, but everything else kind of becomes problematic. So we had addressed the problem of measuring these infinite collections of traces in the past. So we kind of solved that, we proposed our solution to that problem, and we said, okay, let's not measure the cardinality of those infinite sets in those quotients, but let's estimate that cardinality using, well, a notion of topological entropy of the collection of traces. And that's the way we measure it. Well, this is a cryptic formula to just decipher it a bit. B is then the automaton that captures the traces that are present in the collection of traces X, that infinite collection of traces that we want to estimate cardinality of. Then also we do some transformations on that automaton. We short circuit it. Well, that's required for the whole theory to work, but also that's required to actually guarantee that our measures fulfill certain interesting properties. And I'll just demonstrate that in a couple of seconds and talk about that in a couple of seconds. And then Cn of that short-circuited automaton is the set of all traces of length n. right? So that's kind of just to establish the whole formalism that is now shown on this slide. And then you say, okay, but how still you measure it, right? You have some limit superior that you need to establish for the end that approaches into infinity. So how do we measure it? But we use a well-established theory. So what we need to do to measure that quantity is to represent that short-circuited automaton as adjacency matrix, measure its Perron-Frobenius eigenvalue, which is the largest eigenvalue of that adjacency matrix, and that will be the measure of entropy. So we kind of have computational means to precisely compute that entropy value. And then we measure those quotients that I showed to you on the previous slides, not by establishing cardinality, but by measuring entropies of the corresponding set. So for example, model log precision will be measured as M overlap L, and then taking the entropy of that set, and then also divided by the entropy of M. And model log recall will be similar, but will be divided by the entropy of the log. So that's how we measure and address the problem of infinite collections of traces. And then once we did that, what we were able to achieve that our measures were shown to fulfill all the interesting properties of the corresponding classes of measurements. So these entropy-based measures of recall and precision, they satisfy all the properties for the corresponding set of measurements. Just to give you some idea of how these properties look like. So one of them, right, says if we have a log and we have two candidate models, M1 and M2, that describe that log, that we discovered from that log, then precision of model M2 should be less or equal to the precision of model M1, right? So M1 describe fewer extra traces present in a log than model M2, and therefore its precision should be better. Actually, we even shown that our measures fulfill stronger properties. So here we can put a strict inequality, and our measures will still be able to fulfill them. Some technicalities. So let's now come to generalization. And let's take a look at what literature currently understands as generalization of discovered models. So I gave you our approximate definition. Also, if you look in literature, definition I like says that a generalization measure aims to quantify the likelihood that new unseen traces will fit the model. And if you refer to that work by Buijs on this 6 measures, 6 quotients that I demonstrated to you, well, they say that let's measure generalization as a model system recall, right? So it's recall between a model and a system, one of those 6 quotients between model and system. But of course, system is unknown, model and system can be infinite. So how to really measure it is still a question. There are 4 measures currently proposed in the literature. The last one bullet point here is a really recent one. So it didn't participate in the benchmarking, which also demonstrated that our precision and recall measures between model and log fulfill all the properties. But that benchmark demonstrated that there is still a lot to be done in measuring generalization, right? So many properties that suggested to hold for those measurements are not fulfilled by those generalization measures. But of course, the last one was not yet benchmarked, so that's also still to be done. So how do we, right? So main problem now is how to deal with the fact that the system is not really known, right? And what we proposed is to look in the area of computational statistics and to use the Bootstrap method from computational statistics. So let me quickly introduce you this method and then also demonstrate how we adapt it to the problem of measuring generalization in process mining. So in bootstrapping, we are saying that, okay, we have some true population, some population of data, which we actually, cannot grasp in its entirety, because it's just too vast. I mean, for example, let's say we have a collection of all the stars in the universe. That will be our true population. We cannot really measure some property of all the stars in the universe. So then let's do the following experiment. Let's take several samples of that true population. Let's take several samples of those stars, and let's measure the properties that we're interested in for each of those samples, right? And then we can derive the distribution of those samples, so properties of those samples, and then we can then measure statistics of that distribution. We can get, I don't know, the mean value, we can have a confidence interval, etc., etc. So, of course, that's challenging, even if, well, we just taking samples. I mean, imagine taking many samples of stars of the universe. That's kind of very hard. Right, so that's why I also kind of say and highlight this artifacts in a dashed line. I said, so this is not really feasible for us. So, but what Bootstrap method requires, and that we have at least one sample. Well, if you cannot generate many, well, if you cannot get many samples of the data, we should be able to get at least one sample. That's what we kind of hope we can do, at least. So let's take one sample. So one sample of stars, I don't know, 1,000 stars that we randomly choose on the skyline. And then let's estimate the entire population based on that sample. It can be different ways of how you estimate that population. It can be even that you say, okay, my sample is my population, I kind of identity. So sample is taken as a true population. And then once you do that, you measure all the properties of that population, you kind of transfer the problem from the real world, where you cannot really measure things, to the kind of in silico world, where you do everything on a computer. You can kind of control everything. And you can now take all those many samples, right? You can take that estimated population, take many samples of it, and then you can use that Bootstrap samples that you sampled from your estimated population to measure the property that you are interested in, establish the distribution, establish the statistics, and, well, by black magic, and a lot of theory behind that black magic, that estimated statistic through Bootstrap samples will be very much similar to the true statistics. So I just did some exercise yesterday in Excel to demonstrate you how this all works. So let's say we have some true population which has Gaussian distribution, normal distribution, Gaussian curve here. And let's say we are interested to establish the average of that population. I mean, of course, here you clearly see that the average is 0, but assume we don't know that. We don't know the true population, right? It exists, but we don't know it. So what we do in the real world, well, but if we follow that real world path and sampling a lot of samples in the real world, we can take many samples of that distribution. I did 100 samples of 100 values. For each of those 100 samples, I then measured an average, and then built like a histogram, a distribution of those averages for 100 samples, and the average was established to be 0.006, right? So very close to the real value of average for the true population that we don't know. I just emphasize again, we don't know that true population. So I said this is not really a way to go. We will not be able to take 100 or even more samples. Usually we will require much more samples than 100 to estimate measurement closely in real world. So we take one sample, and one sample can look like this, right? So this is a sample of a true population. It's kind of, well, maybe resembles a bit, but also very far from a true bell curve of a normal distribution here. But still, it's one sample out of those 100 samples for which I measured the averages and built the histogram over here in the left bottom corner. So this is one of those 100 samples. So I took one sample and then repeated the bootstrapping for this one sample. So I now sampled 100 samples from this one single sample, build the distribution, and establish the average. And the average was 0.007. So very close to this average, which is the well, average if I measure the samples taken from the true population, and also very close to a real value of the average, right? So that's how bootstrapping works. So just by using one sample, we establish the property of the true population very, very closely, very precisely. And again, I emphasize there is a lot of theory behind it, why this works, and etc. So now let's transfer this bootstrapping method to the reality, to the problem of process mining, right? So this is these three sets that we have. We have a system that we don't know, right? So we have a system. It's highlighted. The borderline is dash, so we don't know that. We know log. We know that we have recorded log, and we know the model that we discovered, of course, from that log. So if we want to measure generalization kind of in the presence of a system and kind of in an ideal sense, what we want to do, we want to sample that system many times, right? We want to sample the system many times, and we want to establish that generalization from those many samples that we constructed from the real system. I know, whatever that generalization measurement is, it's a system model recall, for example, or any other method. And then we establish the distribution, and we can take statistic, we can take average, we can take confidence interval of that measurement, etc. But it's kind of impossible. We don't know the system. What do we sample? But we have, of course, the log, which is one sample of the system, right? It was sampled over some extended period of time, represents the system. We have one sample. So what we propose then to do, so actually the log is that one sample that we need to take. And then we also need to estimate the system traces from that log. We actually take it as identity set. So the log is an estimated system for us. Well, it's kind of also assumption of common assumptions of process mining that log is well, estimates system fairly well, because it's taken for an extended period of time. So it contains a lot of traces, thousands, in ideal case, millions of traces of the system. And then we do everything in silico on a computer, all those bootstrapped samples, and we measure them. For each of the bootstrap sample, we measure generalization, we establish the distribution, and we know the statistic of that distribution. So actually the idea is that we measure generalization as system model recall, but also we say, well, let's also measure system model precision, because kind of these two measures then establish a relationship between model and systems more completely. And we use our entropy measures because, well, those entropy measures can also deal with infinite collections of traces. So our models can describe infinite collections of traces, and well, systems can also be taken as such that describe infinite collections of traces. And then we bootstrap many log samples. We measure, well, actually we measure then model bootstrap log precisions and recalls, so many of those, and we then take average of those measurements, and those averages should estimate the true model systems recall and precision. So that's kind of the idea of the whole approach. And now maybe it's interesting to think, so how do we actually bootstrap those samples? So how do we construct those bootstrap samples? If we look at the theory of bootstrapping, there are three common ways to do that: non-parametric, semi-parametric, and parametric. In a non-parametric bootstrapping, we take our sample and we resample with replacement elements from our sample. So we kind of don't generate any new elements. We just take elements from our only sample according to the distribution of that sample. And then when we take one element and we add it to our bootstrap sample, we put it back so it can be resampled again, so to say. So in the semi-parametric bootstrapping, we kind of say that in real population, we can have elements which are similar to elements that we see in the sample that we have. So they can be different from what we see in the sample. So kind of noise, there can be noise present. in the Bootstrap samples. And in parametric sampling, we say we know that our data comes from certain distribution, but we don't know parameters of that distribution. So then we estimate those parameters from our sample, and then we measure the we simulate Bootstrap samples from the distribution configured based on the parameters estimated from our sample. And well, here for our purpose, we kind of understood that we need a method which will be able to generate something new for us, because probably system can do more than what we've seen in the log, right? We can unfold certain loops, for example, that were not seen in the log necessarily. And therefore, so we kind of took the approach of semi-parametric bootstrapping, and we said, okay, we can breed our traces to generate something new from the log. And we propose this very simple operation of crossover for the traces. So we proceed the following way. We take two random traces from our log. So here, for example, it can be even the same trace. So here we do crossover over two traces where it's the same trace, A, B, 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 C, F. We need to find a common seed. We kind of use a parameter to identify how long that seed should be. For example, here, the length of 2. So we need to see a common gene, so to say, in both traces, BB, for example, and then we take the prefix of the first trace up and including that common seed, and then the suffix of the second trace that follows that common seed. And then we obtain the bootstrapped kind of trace or offspring, or as Aalst, who's also participating in this research, likes to call it offstrings. We obtain offstrings from our event log. And we can cross over either way to get two offstrings here. And you see that these offstrings, they were not in the log, but they happen to be in the system, right? So they're traces of the system. And of course, we want to use such bootstrapping mechanisms that will allow us to obtain offstrings, which are offstrings of a real system. So that's the method we used, and let's bootstrap sample log can then look like this, right? So if we then generate many generations of offstrings and include them into our bootstrap model, so that's kind of the way the bootstrap log can look like. It can contain some traces from the original log, but also some fresh traces. So just to then show you a concrete example. So again, the same system log and model that I demonstrated to you before. So if I measure model system precision and recall between well, this actual system and this actual model that you see on this slide, using this entropy measure, we will get some number. They will both be actually equal to 0.867. So this is kind of a theoretically correct value that we want to observe. But we don't know the system, right? I say system is unknown, and if a system is unknown, of course, we cannot measure those entropy measures, precision and recall. Well, we can do our best bet can be to say, okay, a log is a good representation of a system. Let's use a log. Let's measure model log precision and recall. And see what those values are, and they will be 0.791 and 0.935. So some values which are a bit different from the true model system precision and recall. And if we now use our bootstrap method and we kind of generate, well, more bootstrap samples, and we generate more, these samples are also larger, so to say, then we start to estimate the true values closer and closer, right? So here we took what n is 1 million traces in a bootstrap log. We use 10,000 generations and m of 100 bootstrap samples logs, and then we were able to establish that a bootstrap precision measure is 0.897 and bootstrap recall is 0.908. So they're not exactly the same as the true value, but they're getting closer. So the more computations we invest into this exercise, the closer the values start getting to the real values. All right, so this is kind of the trick that we use to measure generalization. And we did some experiments with well, synthetic data, which is well, partly real world data, but partly synthetic data. We took 60 models from industry. So one of our industry partners shared with us 60 models. We said, okay, these models will be systems, true systems. And we generated random logs from those systems, discovered models from those systems, so kind of obtain this lab environment where we have a system model, we have a log, and we have a discovered model. And then we applied our Bootstrap method. So here in this column, model system measurements, these are the measurements between model and a system if we would know the system. Right, so the discovery algorithm was good. It was always discovered fitting models, but precision values are quite different for those discovered models. Then we said, okay, if we don't know the system and we don't apply our Bootstrap method, what will be the model log precision and recall if you use a log as an estimation of what system can do? And then we obtain these measurements, and then we do it, Bootstrap generalization measures. And for all the experiments, we've seen that our measurements start to get closer, sometimes very close, sometimes not very close, but still closer. So for example, here, right, the true measurement was 0.595. If we use a log, the measurement is 0.482. If we use our Bootstrap method, we start getting closer. Our measurement is 0.553. But of course, sometimes, like we see here, the true value is 0.7. The model log value is 0.244, and if we use our bootstrapping, we're getting closer, but we're still far off. Right, so probably it also demonstrates that better bootstrapping methods needs to be developed for constructing those bootstrap log samples. Maybe we need to invest more computational resources, so this is still work in progress. But anyway, what we were able to observe that the approach works in general. It kind of brings our measurements closer to the true measurement. So we kind of come from full uncertainty to a bit more well, clarity in the picture, right? Of understanding of what our system is. All right, so that's basically the approach I wanted to demonstrate to you and our idea. This is very fresh idea as well. It's still under review, but you can also, it was submitted at the beginning of July to a conference. It's also available in archive, so you can read our preprint. So in this work, well, 3 whales of process mining were involved: myself, Aalst from CIS, and Luciano Garcia Banuelos from Tecnológico de Monterrey in Mexico. So it's a fresh idea with potential, I believe, and we want to explore that potential in future work. You can parameterize this approach by different generalization measures. Well, I showed you 4 measures that exist, right? And our entropy measures, that's kind of the 5th measure here that we introduced. Of course, you can parameterize with different generalization measures, with different bootstrapping mechanisms, and all of these pieces need to kind of compose in a puzzle. Like if you get the puzzle correctly, then the whole system will work, and then these bootstrap measurements will be closer and closer to the real measurements. So currently we did some experiments that so far confirm the feasibility of the approach in general, but of course much more needs to be done. So in future work, we want to do more experiments to understand current breeding mechanisms, actually to study it even better, to kind of have some quality measures, because that bootstrapping, this crossover operations on string can generate traces that fall into the system, but they can also generate some noise, traces that are not coming from a system, right? There needs to be a good balance of how well that bootstrapping mechanism guesses the traces of the system. Well, and also some formal analysis of the approach, what are the formal properties, guarantees of the approach. This is still all future work. that needs to be done. Okay, I want to close here and maybe take your questions at this stage. Thank you for your attention. Yeah, so if you have any questions, it's time to ask them. So maybe unmute yourself because I don't see a chat window. I was not following chat entirely in the course of this seminar. I'm trying to find it. Any questions?
Hi, Artem, thanks for the talk. I have a quick question. When you measure recall and precision, do you use any existing measures from process mining, or it's just like traditional recall and precision, it's either in or out?
It's kind of a traditional way of in or out. Trace in or out. It's just that we were using our entropy versions of that in and out because well, we need to deal with infinite collection of traces, right? Models can describe infinite collections of traces, so we cannot really measure cardinality of those sets. So we were using those entropy-based measurements, entropy-based precision and recall, to establish as proxies to generalization.
But with no partial matching.
No partial matching. Here we were using, so this work on entropy-based measures was quite successful, right? We had several works offsprings of that work where we extended by partial matching of traces, and traces can be different, but here we used exact matching of traces. So even only if traces are exactly the same, they were ending up in the overlap of the sets of compared collections. Yeah.
Hi, Artem. I had a question about slide 24.
Yes.
Yeah. I was just wondering, I noticed that for all of the systems you tested here, the model system recall was 1, like it's perfect recall.
Yeah.
Is there any reason why that might be the case? So it's basically, if I understand correctly, that means the model is describing all of the traces supported by the system.
That's correct. That's correct. That's correct understanding.
Yeah.
There's no particular, well, there's no particular reason. We should have actually we should actually need to do a better job here and well, choose some discovery algorithms and configurations of that algorithm that will also generate models with precision, which is with recall, which is not 1. I don't know. We didn't bother so far. Yeah. So if this is future work, it will be good to see what's happening. It's not that we are trying to hide here. It's just that we had no time to do it yet. So it's future work. Yeah, it will be good to investigate what happens. And this algorithm, we were using inductive miner. We try to play, it's one very established algorithm in the area of process mining. We try to play with some configuration parameters for some time, but at the end we gave up. It was discovering fitting models. We gave up and said, okay, let's stay with these models because these experiments are also time consuming. Right, this bootstrapping is computational intensive. It took us a couple of days to run it. So we said, okay, let's leave with this result so far. But I agree, more experiments needs to be done.
Yeah, and I guess another follow-up question is, it seems like, you know how you had a method for sort of generating novel traces?
Yes.
I didn't really understand how that worked, but it seems like that would be critical to the accuracy of this approach. Is that?
That's totally correct, Neil. You're totally correct. It's critical because we expect that these fresh traces that we generate, they they happen to be the traces of a true system. They can be supported by the true system. And so just maybe to repeat how we do it. So we take a log, we select two random traces from the log. So here we selected, by chance we selected the same trace twice, A, B, B, C, F, right? So here we take A, B, B, C, F, and the second random trace was that trace again, A, B, B, C, F. And then we need to check if these two traces, randomly chosen traces, have some kind of common genetic information in them. So they have some common subsequence. And that subsequence is configured by a parameter, the length of that common subsequence. So if we, for example, take a parameter to be, let's say, 2, right? So BB can be a common subsequence. And that common subsequence is also chosen randomly in those two randomly traces that we have picked from our log. Right, so it have, like, for example, we say, oh, randomly we identify this subsequence BB to be here in the first trace, and it happens that this subsequence happens at this position in the second trace, right? So here is a different position. And then we take a kind of a crossover, we say, let's take a prefix of the first trace up to and including this common subsequence, so ABB, and concatenate it with a suffix that follows that common subsequence in another trace, right? So with CF. So we concatenated ABB with CF to obtain ABB CF. And here we can concatenating ABBB with BCF to obtain A 4 times BCF. Right? So we are getting these fresh traces which show us that possibility of doing well, looping B a different number of times. And kind of this time it happens that these traces are the traces of the system, right? The system can support any number of iterations of trace B. But it can be that well, these fresh traces, these offstrings, they can not come from the system, right? So there is this is a critical point to have this bootstrapping correctly. Well, it's kind of from our understanding of the process mind domain, how processes work. We believe that this is good way to generalize decision points, right? So here was a decision point. After doing BB, we could have done BCF, or we could have done CF. There was a decision point, and we just kind of permutating those decisions. We kind of take a new combination of decisions, right? But yeah.
Artem, if I can jump in, I mean, for what I see, it looks like you're just increasing the observation of the loop. And if the system if the process encodes that loop, you're basically throwing in traces that will, of course, fit. So you are automatically increasing fitness and also precision if you use your entropy measures. How do you justify that? Because you're throwing in traces that are always fitting 100% of the times.
You are correct that this kind of crossover can unravel some loops, but we also kind of believe that this kind of have evidence. This also can come up with a new combination of a chain of decisions. But even if it's not a loop, we can take like the prefix of one trace up to some decision point and a suffix of another trace after the decision point, and kind of combine them in a new way. So it can give you new iterations of a loop. It can also give you new combinations of decisions, but it can increase your precision and fitness, as you said, recall. But it can also generate traces which are not in the system, right? It can also kind of generate a wrong trace. It's particularly can be observed when you work with interleaving of concurrency. And if your seed is this common subsequence that you are basing your crossover on is very short, it can be that you will generate something that was not really coming from the system. So it can also generate some noise. So it works in different ways. If you increase the length of this common subsequence on which you do the crossover, then you have less chance to actually do a wrong crossover on the interleaving, right? So that's why I'm saying this is yet to be explored further, but preliminary results are good. Kind of, they show that in general, the approach helps us to estimate measurements better, right? So there are some caveats, and we need to address them.
Okay.
But very good observation, very correct observations. That's right. Any other questions? Okay, it's also 1 p.m. Then I propose to close this seminar at this stage. Thank you for attending. If you have any follow-up questions, please contact me per email. I'll be happy to answer and have a chat. Thank you very much, everyone.